So looking into the big wave equation, we've got y as a function of position and time. And what's our usual equation there? What sort of function are we talking about?
Sine.
Yeah, it's definitely a sine function. It's also possible to construct it using cosine, but the important thing is we want to be consistent about it. We want to choose sine or cosine and stick with it. And for this class, we're going to be using sine. And the default sine wave is very strict, very straightforward. It's going to have if we have just the sine wave, then where does it start, or how does it start? Like if you just plug in 0 for sine, what do you get?
Zero.
Sine of 0 is 0, so it's going to go through the origin. And then how much, if we're just looking at angle, how far do you have to go in terms of angle to complete one full cycle?
2 pi.
Yeah, so we're going to go to 2 pi, and then halfway between is pi, and then let's split that up into fourths, actually. So pi over 2, pi, 3 pi over 2, and 2 pi. And so what that's actually going to look like then is, let's see if I can do this. So it goes through to a maximum at pi over 2, and then back down to 0 at pi, and to a minimum at 3 pi over 2, back up to 0 at 2 pi. Something like that. Let me shift that a little bit. So there's our default sine graph. But how do we want to modify that? What can we put into the equation to make this not look exactly the same as it does right now?
You can shift it using like plus a certain like y value.
Yeah, if we want to shift this up so that it's not just centered around 0, we can accomplish that by adding something outside the function, plus, let's say, y sub 0, or y sub equilibrium. So y sub 0 represents the value, the center line value that everything's oscillating around. Like if it's going equal amounts above 5 and below 5, then you'd have plus 5 outside the sine function. What else would we want to do to the equation to modify the graph? Like, does every wave start off at equilibrium at 0?
You can use the total phase.
Yeah, we want to be able to modify the total phase to shift it. A phase shift is a shift in when we talk about phase, we're basically talking about the angle that's the input to the sine function. So for instance, when the phase is pi over 2, we're at a crest. When the phase is pi, we're at equilibrium on the way down. We want to be able to modify that phase by having a plus something inside the sine function. And for this, we'll want a phi. So I'll pull that from here. So plus phi. So that lowercase phi is what we call the shift. And this should be functions of x and t. So we're going to want a time term. We're going to want a position term. The thing is, though, time and position are measured in what units of measurement?
Seconds and meters.
Yeah, time is in seconds, position in meters. But in order to apply the sine function to something, it has to be an angle. It has to be measured in radians. So we're going to need a conversion factor. What could you multiply time by to convert it from seconds to radians?
Q pi.
Yeah, the 2 pi represents 1 full cycle worth of radians. But we also want to cancel out seconds. So we're going to divide it by what?
Period.
Yeah,
Period.
we divide by period. The times 2 pi is 1 full cycle worth of radians. Divided by period is 1 full cycle worth of time, the amount of time it takes to complete 1 full cycle. So by multiplying by 2 pi over period, we're just multiplying by 1 full cycle over 1 full cycle, no actual change. We're just changing the units of measurement. And what would be the equivalent for position? How would we modify distance to radians?
Sorry, can you explain the time one more time? How we modified the units?
Yeah, I think of this almost like a conversion factor. Let's zoom in on that a little bit. 2 pi over period multiplied by time. If you look at this in terms of units, time is measured in seconds. Put that in a different color. Time is measured in seconds. Period is an amount of time. It's just the amount of time for 1 full cycle. So that's also measured in seconds. And 2 pi is radians. We wouldn't actually write 2 pi radians. Radians is technically unitless. It's just 2 pi, but it's 2 pi in radian measure. So when you multiply these together, what happens to the units?
Cancel.
Right, the seconds and seconds cancel out. We're left with a radian measure. So time is measured in seconds, but 2 pi time over period ends up being a measurement in radians. And it has to be in radians in order to take the sign of it. And the whole point of this multiplier is you're converting seconds to radians, but you're maintaining the same fraction of a full cycle. Like, let's say 1 full cycle, 1 period is 10 seconds. But let's say only 2 seconds have passed, so time is 2 seconds. 2 out of 10 reduces to what fraction?
1/5.
Right, so 2 seconds would be 1/5 of a full period. When you multiply all this out, you'd end up with 1/5 of 2 pi, which is still 1/5 of a full cycle. 2 pi over 5 is 1/5 of a full cycle. So you're converting a time that's a certain fraction of a full cycle into a radian measure, an angle that's the same fraction of 1 full revolution. So we're converting from time to angle, but we're maintaining the same fraction of a full cycle. Any questions on that so far? So that's where the 2 pi over period times time comes in. And by the way, another way you can write that, 2 pi over period, what's the same thing as dividing by period?
Multiplying by frequency.
Yeah, 2 pi divided by period is the same as 2 pi times the frequency, because frequency and period are just inverses of each other. So we've got 2 pi over period is the same as 2 pi times frequency, which means this whole 2 pi t over period can also be written as 2 pi times t times frequency, or usually 2 pi times frequency times time. So that's sometimes a more useful way to write it. 2 pi t over period and 2 pi frequency times time are exactly the same thing, just written in different ways. They're completely interchangeable. Whichever one is more convenient under the circumstances is the one you want to use. Any other questions on that term so far? And then for the x term, we can do the same idea. We want to convert x, which is measured in meters, into radians. So what could we divide by that would cancel out meters there?
Lambda.
Yeah, lambda, the wavelength. Because lambda, the wavelength, is 1 full cycle in distance. Let me copy a lambda from this page. Lambda. So 2 pi over lambda times x. Once again, the meters cancel out and you end up with a radian measure. And that radian measure represents an angle that's the same fraction of a full cycle that the distance is a fraction of a full wavelength. Like if the distance from the source to the location of interest is 1/4 of a full wavelength, then the angle you get from this is going to be 1/4 of a full revolution. So that's 2 pi times x over the wavelength. And to combine those, we should be adding all these up. Although we usually put a plus or minus here. And why is that? What does that plus or minus signify?
The direction of the wave.
Yeah, the direction the wave is traveling. Because a wave is a traveling phenomenon. It's a phenomenon of motion. And it could be traveling either in the positive x direction or the negative x direction as time passes. So we use the plus or minus to distinguish between those. Plus if it's moving in the negative direction, minus if it's moving in the positive direction. And I think that covers pretty much everything, almost everything about the wave. The only thing left is we want to be able to stretch it in the vertical direction. So how do we accomplish that?
Amplitude.
Yeah, we put this amplitude multiplier outside of the sine function. A multiplier outside of the function stretches it in the y direction or compresses it in the y direction. The multipliers inside the function on the time and the position stretch it in the horizontal direction. So that should be the complete wave equation. That allows us to modify every aspect of the wave we care about. We can stretch or compress it vertically. We can stretch or compress it horizontally to have any period and wavelength we want. We can shift it horizontally using phi, and we can shift it vertically using y naught. Any questions on that?
I have a quick question. Oh, go ahead. Thank you.
Will we be able to cover to identify the direction of the wave? Yeah, we'll give that a try with some examples, figuring out how to find the direction from the graphs. Any other questions on the theory behind this equation before we move on to some examples?
I have a question on just like the general, what each does. So the amplitude stretches it or compresses in the vertical direction.
Mhm.
The y naught is basically the vertical shift.
Yeah,
right?
shifting the whole graph up and down. And that's true for any function. If you add or subtract something outside the function, you're shifting it in the vertical direction.
So then everything within the parentheses is horizontal expansion.
And you could think of that as modifying the time coordinate or the position coordinate, depending on which graph you're looking at.
So the entire thing inside the parentheses has to do with horizontal. Sorry, I didn't hear the last bit.
Yeah, and that whole thing is typically called the total phase. In fact, let's investigate that a little further. This whole thing inside the sine function is called the total phase, usually written as a Greek capital phi. And note that that is itself a function of x and t. And one of the reasons to write it like this is we can rewrite the y function. Y, instead of writing y as a function of x and t, we can write y as a function of total phase. So y as a function of total phase is just amplitude times sine of total phase plus y naught, because total phase is just an abbreviation for all that stuff inside the sine function. And one of the big advantages of writing it like that is that the total phase tells you some very important information. For example, let's say you're at a certain position and a certain time, and you find that the total phase is pi over 2. What is sine of pi over 2 going to be?
1.
Yeah, that should just be 1. So if total phase equals pi over 2, then the sine of total phase becomes 1, which is the highest it can be, which means you get the maximum possible y value. In other words, a crest. Whereas what total phase would give you a lowest possible y value?
3 pi over 2.
3 pi over 2.
If the total phase is 3 pi over 2, then y is the minimum value, because sine of 3 pi over 2 is -1, which is the lowest it can be. So that'll be a trough. So the total phase, and likewise anywhere in between, if you're looking at, for instance, when total phase is pi, let me put this back at the values it's supposed to be, there we go. If the total phase is pi, then you're at equilibrium. If the total phase is 0 or 2 pi, you're also at equilibrium. So the total phase tells you exactly where in the cycle you are, regardless of time and position. And for example, there's going to be many combinations of a position and a time where total phase equals pi over 2. Those all represent a specific crest as it travels along the medium. So if you have time passing and position changing in a way that doesn't change the total phase, that means you're watching a single crest or a trough or whatever as it passes by along the medium. And this is very useful for comparing two waves. If you're looking at two waves occupying the same space and you want to know, are they both at a crest? Are they both at a trough? Are they both somewhere in between? All you need to do is look at the total phase of each one and compare the results. You don't need the rest of the equation. If all you care about is it at a crest? Is it at a trough? Is it somewhere in between? You can just look at the total phase alone, and that'll tell you where you are. Any other questions on that so far?
I was wondering, in the first equation that you have up top, does the phi that you have within the parentheses, is that like initial phase, or like sometimes the reason is like phi naught?
Oh, the y naught at the end?
Oh, not the y naught, but the one next to it in the parentheses.
This phi?
Yeah.
Or what do you mean?
Sometimes I see like phi written with like a small 0.
Oh, yeah, sometimes it is. It's not so much the initial value of phi, it's more that if you take a look at total phase, so looking at this whole equation for total phase, if you actually plug in 0 for x and 0 for t, what do you get?
Oh, the phase at 0, 0.
Yeah, which is just little phi. So that lowercase phi ends up just being the value of total phase when position is 0 and time is 0. So sometimes that lowercase phi is written as phi sub 0. Phi sub 0. Because it specifically does represent the total phase when the position and time are both 0. And in that context,
Okay,
it does have, it's not exactly the initial value of y, it's really more the initial value of the total phase, but it does represent information about the initial value. It represents what's going on at time 0, position 0.
Okay, thank you.
For example, if at time 0 you've got a crest at position 0, then the total, or the phase shift, the phase constant has to be pi over 2. But it's usually not very easy to see the phase shift value, the phi 0 value from the graph. It's usually easier to calculate that algebraically after you've figured out everything else. Any other questions on the equation so far? All right, let's try out an example then. I'm going to copy this equation and let me see if I can pull up some graphs. I just took a picture of this one from handwritten, so it's going to be a little blurry, but I think, is this clear enough? We got these two graphs. Wait, that's actually. Let me grab a different one. Okay, so here we've got a position versus y graph and a time versus y graph. It's a little blurry, but I can pull the numbers from it if we need more detail. So the position graph, actually both of them go as far down as 10 as a minimum and as far up as 60. So minimum value of 10, maximum value of 60. And what these actually mean, if we look at each one of these individually, like let's say we're looking at x versus y. X represents how far you're going or how far you're looking along the medium itself. Like you can, like 2, 4, 6, 8, 10, you can interpret that as 2 meters from, maybe 2 meters from the source, or just 2 meters from a location we're calling 0. The reference point, the 0 value, doesn't have to be the source. It's just 2 meters away from some location we're calling the origin, 4 meters away from that location, 6 meters away, and so on. So this X versus Y graph is showing all locations along the medium, but only one single instant in time. So that's usually interpreted as a snapshot, like a still photograph of the wave. If you imagine you've got a video of the wave moving and you hit pause, at that instant, the shape of the wave is the X versus Y graph, because it's showing the height at every location along the wave. So you could think of this as like a cross section of the surface of the water frozen at one instant in time. So that would be the X versus Y graph, a snapshot of the wave at one instant in time. Any questions on that so far? And then the other graph is showing all times. The T versus Y graph is showing all instants in time, but only at one position. So this is talking about what's happening as time passes. But instead of looking at the entire surface of the medium, we're just looking at one location. If this is like ripples on a pond, maybe you're looking at just one patch of water. Maybe you've got a little toy boat on the water there, and as the wave passes, that boat is moving up and down with the swells. So this time versus Y graph is showing the history of that patch of water or that piece of rope or cable or whatever as time passes, but only at that one location. And the reason we're doing this is because Y of X and T is really a three-dimensional graph. If you had an X-axis and a T-axis and a Y-axis, you could graph the whole thing. But it's often easier to look at just a single two-dimensional cross-section at a time, X versus Y at one time, or T versus Y at one position. Any questions on the meaning of that so far? And you really need both graphs in order to get a complete picture of the wave. If you had just one of these graphs, you'll be able to figure out some of the information, but not all of it. So let's see if we can use these graphs to build the equation. We know we want the general format to be this. Let me make that a more visible color. There we go. So here's the general format we want this graph to have, or this equation to have. And are there any of these parameters, because we're going to need to find values of all of these, A equals, period equals, wavelength equals, phase shift, and why not? Are there any of these values we can measure directly from the graphs?
Amplitude?
Yeah, amplitude we can get by measuring what?
The crest and the trough.
Yeah, if we measure between the vertical displacement between crest and trough, so that's going to look like, let me actually draw in these lines here. So it looks like this one goes as far down as 10 and as high up as 60. So how far is it between those? What was that?
Would it be 35?
How'd you get the 35?
Because normally when I see that like the trough is not at 60 as the crest or vice versa, I would just add the crest to the trough and divide it by 2.
So if you add two numbers together and then divide by 2, what are you actually calculating there?
Average.
Yeah, which actually means that's the halfway between value. The 35 is going to be the center line halfway between highest and lowest points. So we can certainly say that that center line is at 35. But that's not the amplitude. That's what value in the equation. Which one of these parameters tells you the center line?
Why not?
Why not?
Yeah, that's the value of y naught. Because y naught is the average intermediate value that everything is oscillating around. So 35 is going to be the y value halfway between highest and lowest y values. So that's going to be the amplitude, or the y naught value, the vertical shift. Because if you didn't have a vertical shift, everything would be oscillating above and below 0. What we've done is we've shifted the graph up, so it's oscillating above and below 35 instead. So that's y naught. And we can actually use that to find the amplitude, because amplitude should be the distance between, let's say, this distance here. How far is that? From 35 all the way up to the highest point.
25.
25.
Yeah, so the amplitude here is going to be 25. Because it's 25 as the distance between highest and lowest points. Or no, not highest and lowest. Highest point and equilibrium. So one way of calculating the amplitude, once you've already calculated the intermediate point, the halfway point, amplitude is the distance between that intermediate point up to a crest, or from equilibrium down to a trough. So this distance downwards to the trough from equilibrium would also be 25. And what is that distance between highest and lowest points that we were looking at earlier? From 10 to 60, how far is that?
50.
Right, from 10 to 60 is 50 units. So one way you can calculate the amplitude is the distance between lowest point and highest point in terms of y values, but then take half of that. So you could subtract 60 minus 10 and then take half of that, and that would be 25. Or you could calculate the average value, the y naught value first, and then measure from there up to a crest or from there down to a trough. Either way, we get amplitude is 25. And that should have units attached to it. I just didn't have units written on this graph. But that's presumably going to be 25 meters or 25 centimeters or whatever distance y is measured in. Or if you're talking about a sound wave, it might be maybe 25 pascals. Maybe we're measuring not distance, but maybe we're measuring how much the pressure is oscillating above and below atmospheric pressure. But whatever the units of y are, that's going to be the units for amplitude and y naught. Any other questions on that so far?
Yeah, I think I've realized. So if the graph had crossed the equilibrium point, then it would work for the amplitude. Let's say the amplitude was 60 and negative 10. Would then be okay to add the two and divide it? Because
technically you would still be subtracting. Like if it went up to 60 and down to negative 10, you'd be subtracting 60 minus negative 10, which would be 70.
Okay.
But generally, if you want to know the difference between two values, you'd be subtracting. Just be very careful about which values are positive and which values are negative.
Okay.
Any other questions on the y values so far? And what about the other values? Are there any ways we can find period or wavelength or phase shift from these graphs?
You can find period on the y of t graph and lambda on the y of x. Yeah,
because those are basically the same information, one full cycle worth of time, but versus one full cycle worth of position. So let's try both of those. For the time graph, usually for a period, you want to measure the amount of time from what to what?
We can do crest to crest or trough to trough.
Yeah, crest to crest or trough to trough would be one full cycle. That's usually the easiest way to look at it. Or sometimes you can go from like equilibrium on the way up, forward one full cycle to the next equilibrium on the way up. That would also be one full cycle. In this case, though, it looks like the time graph doesn't really show one full cycle of anything. We can't go from crest to crest because the graph doesn't show two crests, and likewise, it doesn't show two troughs. But one thing we can do is look for a certain predictable fraction of a full cycle. If we just look at, let's say, from here to here, from equilibrium to equilibrium, that's how much of a cycle?
Half.
Yeah, that's exactly half of a cycle. Because one full cycle would be equilibrium to crest to equilibrium to trough to equilibrium. If we've just gone from equilibrium to crest to equilibrium, that's exactly half of a cycle. And that's, how much time is that? It looks like from 1 to 4. So we can say 3 seconds equals half of a period, period over 2. And so by writing down a convenient predictable fraction of a period, we can now solve for period by doing what? If we know that 3 seconds equals half a period, how could we isolate capital T there?
Multiply by 2.
Yeah, if we just multiply by 2, we get 6 seconds equals 1 period. So even if you can't really pick out exactly one full cycle on the graph because the graph isn't showing enough information or isn't really showing enough detailed numbers, as long as you can pick out starting at any points of a convenient predictable fraction of a full cycle, then you can use that. Or even if there's not enough information to get one cycle, but maybe you can see that like 3 cycles start and end at marked numbers. You can say 3 times the period equals whatever distance or whatever time, I mean, and then once again solve for period. Either way, in this case, we get period equals 6 seconds.
I have a question.
Mhm.
I don't really understand like how you found it, like the part you highlighted in pink and then what you did afterwards.
What I highlighted here was exactly half of a cycle. Because if you take a look at the default sine graph, if we just go back to, let me draw that out again. If we just have the most basic fundamental possible sine graph, that is this would be one full cycle. If we go from equilibrium up to a crest, down to equilibrium, down to a trough, back up to equilibrium, that's one full cycle. But what we're looking at here is just half of a cycle. Because we're not going through the entire cycle, not through the entire process, just half of it.
How do we know specifically that it was half?
What was that?
How did we know specifically that it was half?
Just based on where we started and where we ended. That we're starting at equilibrium, going up to a crest, and then back down to the next equilibrium. So if you compare that to the original sine graph, just y equals sine of x, equilibrium to a crest back to equilibrium is only half of a cycle. If we also continued down to a trough and back up to equilibrium, that would be the other half of the cycle.
Okay, so is it just that any 2 points that are at the same spot, right, are considered half that cycle?
Not necessarily, because for instance, if we took like this point and this point, this span here would be much less than half a cycle. The important thing is we're going from equilibrium to crest to equilibrium. And there are other half cycles you could use as well. For instance, if you can't really, even if there's not really easy equilibrium points to mark, if you instead go from, let's say from a crest down to equilibrium and then continue down to a trough, that would also be exactly half of a cycle.
Okay, yeah, I get it now. I think I was having trouble seeing it because the equilibrium wasn't at 0.
Yeah, it doesn't have to be equilibrium. It's just if you can specify this region of the wave is exactly half of a cycle or exactly a fourth of a cycle. For example, if we looked at just this part, like from a crest to equilibrium or from equilibrium to the next trough or something, that would be exactly a fourth of a cycle. So you could say this much time, however much time that is, equals period over 4, then multiply by 4 to get the full period. As long as you can identify a predictable fraction of a full cycle, then you can solve for one full cycle.
Okay, so we said that, so since we know that this is half the cycle, we're basically setting, what was the 3 again?
3 seconds was the amount of time, because this section of the wave I've highlighted in pink starts at 1 second and ends at 4 seconds. So from 1 second to 4 seconds is 3 seconds worth of delta time. So we know 3 seconds is exactly half of a period. Multiply both sides by 2 and we get 6 seconds.
That makes sense, thank you.
And we can do a very similar thing for position. If we had 2 crests or 2 troughs, we could just measure the amount of distance from one to the other. In this case, it looks like the crest is a little bit before 0, so we can't really see exactly where that is. But I think in this case, it's going to be more convenient to look at, let's try that fourth of a cycle approach. If we go through exactly a fourth of a cycle from, let's say, from equilibrium up to a crest. It looks like that's going from 8 meters to, and this looks like halfway between 10 and 12. So from 8 meters to 11 meters. So that's 3 meters. And we can say 3 meters is, and what fraction of a full wavelength is that?
A quarter.
Yeah, that looks like exactly 1/4 of a wavelength. So wavelength over 4. And then how would you solve that for wavelength?
Multiply by 4.
Multiply by 4 and we get 12 meters. And in fact, if we take a look, if we try doing 12 meters, 12 meters will be something like this and a little bit beyond. Because from -1 to 11, that would be from crest to crest. So presumably the crest is at -1, just before 0. So we now know the wavelength, 12 meters. Any questions on that so far? So if we fill all that in, what's the only stuff we still don't know about this equation?
Phase constant.
Yeah, we don't know the phase constant. And also we don't know the plus or minus. So we're going to need to figure out which direction it's traveling. So we should also treat that as an unknown. Direction equals, we don't know. To find the direction, because that's really the next step we want to do. We can't really do the phase shift until you know everything else about the wave. But to find the direction of travel, let me tidy up these graphs a little bit.
How would you find the full wavelength? Like, I know you did math, but like looking at the graph, how do you know like where the wave starts and ends?
You can start and end at any point on the cycle as long as it's the same point on the cycle. For instance, in this case, I think since this graph shows more than 12, more than one full wavelength, we actually could use a full wavelength. We just wouldn't be able to start on a crest or a trough because it doesn't show 2 crests or 2 troughs. What we could do though, let's say we look at, like this point right here is, we've got a point right here that is equilibrium on the way down. If we look forward, we get equilibrium on the way up won't do it because equilibrium on the way down and equilibrium on the way up are 2 different types of points. But we do have another equilibrium on the way down over here. So if you take a look at the graph from here to there, from equilibrium on the way down at 2, down to trough, back up to equilibrium, to a crest, back to a trough, or back to equilibrium on the way down at 14. This is one full cycle because it starts at equilibrium on the way down and ends at equilibrium on the way down. Same type of point. That's from 2 to 14. So how much distance is that?
12.
So we really can say the wavelength is 12 here. That is one full cycle. As long as you're starting and ending at the same type of point, then that's one full cycle. Any other questions on that so far?
For the wavelength, don't we have two crests? One like as soon as the graph begins, and then the second one?
At the very beginning of the graph, that's not quite a crest because it's not actually at 60. The crest is a little bit before that. If you backtrack, it turns out that crest is actually at x equals -1, not at x equals 0. So be careful about that. You don't want to accidentally call something a crest or a trough that isn't really a crest or a trough. You want to be sure that that really is the lowest it gets or the highest it gets. And for that, it's a good idea to look at the slope of the tangent line. Like at a true crest or trough, the graph will flatten out. The derivative at that point is 0. If the slope is still not quite 0, that means it's not really a max or a min. So let's see if we can figure out the direction of travel here, because that's the next thing we're going to need to know in order to choose plus versus minus. And for that, anything involving motion, whether it's direction of travel or speed or anything like that, you really need to compare both the position graph and the time graph, because motion involves position and time. And to compare these, you want to be able to find a single point on both graphs that represents the same information. Like for instance, this position graph represents all positions, but only one instant in time. And what is that instant in time?
2 seconds?
Yeah, this whole graph represents 2 seconds, but all positions. So what we want to do is we want to find that time on the time graph. So 2 seconds on the time graph looks like it's right there. So that's 2 seconds. And likewise, the time graph represents all times, but only one instant, one location. And what is that location?
X equals 10.
Yeah, so we want to find that location, x equals 10, on the position graph. And we have that right here. So if we take a look at those 2 points, specifically this point and this point, those 2 points represent the same information, just drawn in different ways. In fact, if you take a look at the coordinates there, it looks like this point has an x coordinate of 10, because that's where it is on the graph, a t coordinate of 2, because the whole graph is at t equals 2, and a y coordinate of, looks like about 55. And I'm estimating there, but close to 55. Whereas if we look at the other point, this point on the t graph has a t coordinate of 2, because that's that point on the graph, an x coordinate of 10, because the whole graph is at x equals 10, and a y coordinate of, looks like about 55. So even though these points look different, they represent the same information, they have the same coordinates, they're the same point, even though they are drawn in different ways. Any questions on the comparing those 2 points so far? And if we want to tell the actual direction of travel, we want to figure out, we know this point is at y equals 55 right now. We want to figure out what it's going to do next. So we take a look at the time graph. At the time graph, it's at 55 right now at 2 seconds. If we go a little bit forward into the future, is that point on its way up or on its way down?
Up.
Yeah, the positive slope of the time graph tells us as time passes, this point is rising. So this is at 55 on the way up. Going back to the other graph, we know this has to be at 55 on the way up as time passes. Now let's take a look at the graph itself. Because the important thing is the graph is going to be moving. The point itself doesn't shift left or right. The point itself is just bobbing up and down. But if we take a look at the graph, or at least a portion of the graph, let me draw that thicker. So we want to be able to shift this graph, either shift it to the left or shift it to the right. And we know that this point needs to be on its way up. So if this point needs to be moving upwards, would the graph itself moving to the left or right allow that to happen?
Yes.
Left.
Yeah, if we move this graph a little bit to the left, a crest is approaching this point. So it's going to shove that point upwards. Move it a little more to the graph a little more to the left, and the point gets shoved even further upwards until we get to the crest, of course, and then it starts moving down. But the important thing is, in the immediate future, the graph moving to the left causes that point to be pushed upwards. If we tried it the other way, if we tried moving this graph to the right, the graph moving to the right would cause this point to sink downwards, and that's not what we want. We want the point to move upwards. The only way that's going to happen is if the graph moves to the left. And if you find that difficult to visualize or difficult to draw out, I also find it useful to look at it in terms of the nearest crest and the nearest trough. If we want this point to move upwards, should we expect the nearest crest or the nearest trough to move towards it?
Crest.
Yeah, we want the nearest crest to move towards it. Nearest crest is here and needs to move to the left in order to move towards that point. So the nearest crest has to move towards it to shove it upwards. That means the wave itself is moving to the left. So we know the direction is moving to the left. Any other questions on that so far? And at this point, we should be able to fill in everything we know. The amplitude is 25. The period is 6 seconds. It's moving to the left, so we should use plus instead of minus. We know the wavelength is 12 meters. We know the vertical shift is 35. So we now have all the information about this wave except for phi. And to calculate phi, all we need to do is plug in any point on either graph. Because if you can plug in values for x and t, then we can actually solve for phi. And any point will work, but a crest or a trough is going to be the most convenient. So what would be a crest or trough that would be easy to work with here? Do we have any crest or trough where we know the numbers?
You have 11 for X and looks like 2.5 for T.
Well, we don't want to look at a crest on both graphs. We want to look at just one crest on one graph. Either one will work. But let's take a look at that x equals 11 that you mentioned. If we take a look at x equals 11, right here, that's definitely a crest. So we have a crest at x equals 11, t equals, what's the time value for this entire graph?
2.
2, yeah. So if we plug in 11 for x and 2 for t, that should give us a crest. And what should the total phase equal if we're at a crest?
Pi over 2.
Over 2.
Right. Total phase equal to pi over 2. If we take that total phase, 2 pi t over 6 plus 2 pi x over 12 plus phi, and set that equal to pi over 2, and we can now fill in, we know t is 2, we know x is 11, We now have an equation with, what's the only unknown left here?
Phase constant.
Yeah, so you can now solve that for the phase constant. Plug that back into the original equation, leaving x and t as variables because we want y to be a function of variables x and t. But plug in the phi value and you now have your complete equation for the wave, which you could then use to predict, for instance, the height of the wave at any position at any time. That equation fills in all the information about the entire wave.